I'm at the Institute of Geophysics, Polish Academy of Science, and I'm a researcher there. I've started my research into Snowball Earth during my PhD, which I just finished recently, and which I will actually continue during my stay at the Institute of Geophysics. So I got asked to do this lecture, and I hope it's the first of many. So I will be presenting a lesson about Snowball Earth and basically what it is and how it was formed and how we know that it actually happened. And so hence the title, Snowball Earth, How, What, Why, and When. Now, when we think about a Snowball Earth, we think about a planet that is basically covered in glaciers, and these glaciers can extend across the whole Earth. And when you actually think about it, it's kind of like a day after tomorrow's scenario, if you remember the film. And what is interesting about that is it's very different from the world we know today. The world we know today is, of course, heating up, and we have climate change. And of course, there's always been climate change, but of course, the pace of which is happening today is very rapid, and it's heading not towards the cold Earth, but towards a much hotter Earth. And but it wasn't always like this in Earth's history. And of course, there were various points in time when we had no ice, and of course, there were times when we had a Snowball Earth scenario, in which we had a complete ice covering of the whole Earth. So just to show you this image of, which is from NASA actually, of what a Snowball Earth potentially looked like. And why that's interesting is if you look and compare it to Europa, for example. Europa is a moon of Jupiter, and of course this is a world which is completely covered in ice as well, and it doesn't have an atmosphere. That's the one significant difference between Europa and Earth, of course, but it is an ice-covered world, and NASA actually is actually planning an expedition to Europa, and they aim to actually try and get beneath the ice and maybe see what lies beneath, because this has a lot of interesting consequences for our own scenario. Because as I'll show you in this lecture, we can actually see how the world has changed for our benefit as a result of a Snowball Earth scenario, and how various things have changed and been very beneficial towards us, and certainly the evolution of life as we know it as a result of Snowball Earth scenario. So before we actually get into that, I want to ram home a fundamental aspect of what we're dealing with, and that is, of course, deep time. And of course, we know that the universe is more or less 13 to 14 billion years old, but our world has only existed for 4.5 billion. And of course, maybe that seems like an almost inconsequential number, but it is very significant. And if you think of the Earth through the diagram which I've showed you here, in that we have 4,500 million years of Earth's history, and humans, if you actually had to take it as an hour clock, we've only existed for the last second. And I've put a little red at 0 and 0 there, which is where humans have existed. And that red line is probably too big, actually. And you can see we have different points in time. We have the Phanerozoic, the Proterozoic, Archean, the Hadean existing. And of course, life, as we know it, has only really existed in the Phanerozoic. And what the Snowball Earths I will be talking about are actually existed before the Phanerozoic. So from 700 million years ago, approximately, was the last one. And there was actually one documented about 2.4 billion years ago as well. And we will get into that. But I just want to emphasize that this happened a long time ago, but it still has a bearing on what is happening today. So just to highlight what has been going on during human history, of course, is that, of course, if you look in recent time, which is called the Pleistocene or the Quaternary, we have, of course, at the present, where we have ice at the poles. And of course, if you go back 20,000 years, obviously the ice sheets extended much further to the south. We had in Europe and North America particularly very large ice sheets which covered large parts of the world. But of course, compared to a Snowball Earth, it's actually nothing. And of course, the sea level, because so much ice was actually in these glaciers and ice caps, it was about 130 meters lower than it is today. And of course, this is part of a cycle. So we have ice ages and we have times like the present. And if you look back to 400,000 years ago, we've had at least 4 ice ages. And ice ages are pretty significant things, but of course, compared to a Snowball Earth, they're not really much at all. So these sort of scenarios have existed, but of course, not a Snowball Earth scenario. So to get back further into time, we're going to go, I'll show you how it looks back all the way back to about 800 million years ago. And of course, this chart, which I show you here, is so the age down the bottom there is up to 800 million years ago. And of course, I've given paleolatitude. So this is latitude that existed during time. And you'll see that particularly throughout the whole of the Phanerozoic, which is the period of life as we know it on Earth, there hasn't been any global glaciation. We've had glaciations, but they've never got further south than, more or less about 30 degrees north and south of the equator. But if we go back to 700 million years ago, well, things start to change. We have the Sturtian and the Marinoan, and perhaps even the Gaskers glaciation, and they spanned the whole range and breadth of latitudes which we know today. And that's pretty significant, and we'll see what sort of role that plays through time. Now, of course, I talk about these glaciations, and of course, they're very significant, of course. But what is the evidence for this? Because obviously all the snow and ice and the glaciation itself has gone. And what we're left with is a rock record that actually preserves this type of deposits. And I'll show you what those are. So just to show you how the rock record can preserve it, well, when we have glaciation, we of course have glaciers which actually exist on the continents as well as on the sea as well. So just to show you in these type of diagrams, when you have ice sheets, the ice sheets will obviously grind into the rock which is beneath it, and this will produce a till, which is a very gravelly, almost kind of like what you see on a road. And then, of course, these ice sheets will extend out into the ocean, and they will carry bits of the debris out into the ocean. If they melt and fall, they will, of course, leave these relics on the ocean floor as well. And, of course, in the actual ocean itself, because you're effectively stopping all runoff from rivers, because the rivers are, of course, all frozen, they leave mud, and this mud is pretty special stuff as well, and I'll show you some examples of that in the next couple of slides. So probably the most obvious pieces of evidence you'll see is actually diamictite, and diamictite in itself is not a glacial deposit. You can form diamictites in varieties of ways. For example, when you have mudslides, these produce diamictites or turbidites in the ocean. But a diamictite is essentially, it's a very poorly sorted rock. So if you look in the picture here, you'll see lots of fine grains, but then you'll also see little pebbles and boulders which are actually still preserved. And these, of course, are what defines a diamictite. But and of course, that's very characteristic of glacial deposits. But you have to have something which can prove that this diamictite actually formed in a glacial environment. And what those are, generally, if we go to the next slide, one is striations. Striations are only really formed on glaciers on land. So when these glaciers move across the land, they of course grind into the rock, and these rocks make these striations. So if you look at this picture, you can actually see these scratches on the rock, and these of course formed through the glacial action which we see. And of course, there are other features. For example, when we're talking about marine sediments in a glacial time, we have dropstones. So these are this debris which is brought from the continent into the ocean on icebergs, which then melt and fall, and they fall into the mud, and they make these dropstones. And these dropstones, as you can see, as they fall into the mud, you can see they actually disturb the sedimentary layers which you see. And that's pretty significant in that we know that they've obviously fallen from above and they've since been covered over by this more finely laminated material, which you see in this picture. Here is another dropstone. This is a particularly interesting one, and this one shows the sediment which you actually see in the bottom of the oceans during a Snowball Earth. You'll see it's very laminated, very layered, and this is actually very fine sediment which actually accumulates in the ocean. We'll talk a little bit more about this a little bit later on, but it's very significant because you can actually see how the dropstone is actually bent or distorted the sedimentary layering which you see there. This rock is of course red, and the reason it's red is because during a Snowball Earth, the ocean actually, the circulation in the ocean basically gets shut off. So you don't have any mixture which you see in the ocean anymore. And because of that, it allows elements like iron to build up in your ocean, which of course then deposits chemically and it forms iron formations. We'll talk a little bit more about that later. But these are the definite characteristics which you can see for glacial deposits. But of course, in order for it to be a global glaciation, it of course has to be seen globally, of course. And of course, if you look on this picture of the global distribution, you can actually see all these glacial units which are preserved in the rocks. Now, of course, using geochronology, which is the ability to age date a rock, we actually know the age. And for example, these older cryogenian Sturtian glaciations, they were deposited 730 to 700 million years ago. And we know these ages through age dating. And you can see that they're widely distributed across the world. Of course, a lot of the crusts that we see today, some of it wasn't formed during this time. So you'll only ever see these glacial deposits on very old pieces of crust. So, for example, most of the crust which we see in Europe is actually quite young. So you can only see that in Svalbard and in Greenland, these rocks in Europe. But of course, on these old terrains in North America and Africa, for example, Australia, you can see quite a few of these. Of course, as I showed you in previous slides, that there was actually two glaciations. So this is the younger. This is not the Sturtian glaciation. This is actually the Marinoan, which occurred slightly younger in time. One of the things you'll see on the last two slides, you see the symbol BIF, that stands for banded iron formation. We'll get into what that exactly is just shortly. But you can see how big these deposits are, and that's pretty important when we talk about other aspects of this glaciation. Now, I've shown you some geological evidence, and this is very good, very characteristic of glaciations. And of course, so the first question is, okay, so we have a lot of deposits, and they're distributed throughout the world. It's good evidence, of course. But do we know that any of these land masses were at the equator at the time? Because that's pretty important, because as we know, the continents move around, and of course, these could have all been at the poles. And certainly, when we look at these glaciations in the Phanerozoic, our current era, most of them all occur at the poles. They don't occur in the equator unless they're in mountains. But we've actually had a look, for example, at the Sturtian glaciation, and I've got an image here of North America. It's in blue, and I've got this old pink core is actually the continent that existed 710 million years ago. And you can see these Sturtian glaciation events where they've been documented in North America. And you can also see some flood basalts, which are pretty crucial when we talk later about the causes of Snowball Earth. But you can see that North America at 710 million years ago was obviously a lot smaller, and it was formed all over the equator. So not only are these glacial events pretty global, and we know that they're glacial, but they also were deposited on the equator. You won't really expect that to occur in the present day, of course, to have such large deposits of the equator. And we know this through paleomagnetism, and I'm not going to go into paleomagnetism or geochronology today and its fundamentals, but we can perhaps leave that for another lesson. But all that needs to know is that geochronology and paleomagnetism show that these deposits were deposited on the equator, and that in effect is good evidence for global glaciation as well, because it's just too warm in the present circumstances to have glaciation there. And one of the other features I talked about that there was almost all the continents, or the continents that were preserved from this time, were actually also part of a supercontinent. And I've given you an example of what the paleogeography looked like for Earth at 750 million years ago. And you can see different pieces of crust. And of course, you probably won't recognize many of these names. You have LA is the biggest there. That's Laurentia, and that is, of course, the core of North America. We have Baltica there as well, BA, and you'll see that sitting right next to it. And the Baltica is the oldest crust in Europe. And we have lots of other fragments, which you can see there. For example, India, of course, we know today Siberia, which was also there as well. And you can see that this supercontinent that existed, kind of like Pangaea did in the Phanerozoic, was straddling the equator, and it wasn't at the poles at all. So the fact that we preserve these glacial deposits from this time on the equator in part of a supercontinent also demonstrates that this is a Snowball Earth scenario. Just to further illustrate what this supercontinent looked like, this is when it came together at 800 million years ago, and this supercontinent was termed Rodinia. So what we see is that all the continents basically collided into one body, and these form these really giant mountains, which we see preserved from this time, which mostly occurred between 800 and 1,000 million years ago. And that is, of course, these mobile belts, which I demonstrate in this figure. These are old mountain belts, and they've long since been eroded, and we only see the roots of them preserved today. But you can see some outlines. If you look at Baltica there, you can actually see where Scandinavia is, and you can see Poland would actually basically be on that piece of crust. And then, of course, we've got Australia and Congo, India, all preserved within the supercontinent. And that's backed up with both geological evidence and paleomagnetic implications as well. And although we don't know some of the exact configurations, we're pretty certain of most of what you see there now. So, having shown you where the Snowball Earth happened and at what time and what's the evidence, I will just show you very briefly here how you actually start and end a Snowball Earth. So basically, once you assemble this supercontinent, you actually supercontinents, because they're so heavy, they always tend to drift towards the equator. And once they're at the equator, they're only stable for a certain period of time. They create a kind of anomaly in terms of how heavy they are. And because of this, it doesn't make them stable. So they always tend to want to break apart. And as they start to break apart, you see lots and lots of volcanism, kind of like what you see in the East African Rift today, but on a much larger scale. We're talking about, you're almost actually covering whole continents in volcanic material. And when you actually cover these whole continents with volcanic material when they're at the equator, they of course weather, and they deposit into the oceans. And when you do this, all the carbon dioxide in the atmosphere at that time gets drawn into the oceans during this weathering process. And this, of course, starts the whole Snowball Earth procedure. And as you start cooling down the Earth, it also starts reflecting sunlight. This is a term we call albedo effect. And this, of course, leads into this whole Snowball Earth event, which you see. So that's demonstrated through 1 through 3 there. And there at number 3, we're at the peak of the Snowball Earth. Now, of course, the volcanism continues. It doesn't stop. And because of this, we start to build up carbon dioxide again in the atmosphere. And in the oceans, we're also depositing iron formations. And, of course, the whole ocean cycle gets shut down. And as we begin to build up this carbon dioxide again, it basically releases the Earth from the Snowball Earth, and it starts melting. Now, there's a little bit of controversy over how quick this happens, but generally it's foreseen that it happens extremely quickly. Same happened actually during the Ice Age. The glaciers retreated from Europe and North America extremely quickly. And in the immediate aftermath of a Snowball Earth, you basically completely melt all the ice on the planet very, very quickly. And you see carbonates, for example, at the poles, which are generally only deposited in equatorial regions. And then, of course, after this sort of yo-yo effect, you basically come back into a normal present-day type of scenario. And that's how you basically see the whole Snowball Earth playing out in terms of time. Now, a lot of that is still not very well understood about the whole modeling procedure and how this all happens. But I just want to get quickly into how significant this all is in terms of the implications, because like I said, most of the example which I demonstrated to you was at 720 million years ago. But we also see that a Snowball Earth occurred 2.4 billion years ago, 2,400 million years ago. And this is called the Paleoproterozoic. And of course, there was no life as we know it during this time. So just to look at this diagram, which I've showed you, we start off at 4 billion years ago when we had the formation of the Earth, and it all came together. There was large amounts of volcanism, and we saw lots of asteroids impacting into the Earth. And during this time, the Earth was more like Venus than it was today. And of course, the first life forms started to evolve during this time, mostly bacteria and archaea. But then, of course, through time, we actually see the first glaciation happen, global glaciation, and that occurred 2.4 billion years ago. And during this time, life as we know it didn't really exist that much, but we had large deposits of iron formation, and the continents, just like at 720 million years ago, they came together. And when these continents came together, they also wanted to break apart, just like later. And we saw that during this time, we actually see the rise of oxygen. And that is, of course, deeply connected with the Snowball Earth, as well as the supercontinent and all these volcanic events happening. And then, of course, through the next billion years, nothing much happens. And then at 720 million years ago, we see the same thing happen. And we have a supercontinent at the equator. It begins to break apart, a lot of volcanism, these global glaciations. And after it, we see the subsequent rise of oxygen levels. And that is tied, of course, to the rise of multicellular life like we know it today. And of course, by the time you get to the Phanerozoic, you have oxygen levels at 20% of what portion is in the atmosphere, which is of course what we know today. So just to expand further on that, that's the next slide. We actually see during the Archean, so 3,000 million years ago, we see archaea and bacteria. Then we have this first glaciation, global glaciation, and that produces these, after that we have these eukaryotes, and we have the rise of oxygen to 1% of present day levels. And of course, during this time, we have lots of deep water, sulfides, and this helps produce the iron formations. And then, of course, when we get to about 720 million years ago, we have the further rise in oxygen, and that is when, of course, multi-cellular life begins to take off. First with the metazoa, so this is more like jellyfish and this type of things, and then, of course, plants and that type of things, which lead further into the world we know today. So as you can see, there are lots of implications for these snowball Earths, and although life may be difficult during the global glaciation, certainly at the end of them, there's certainly lots of nutrients in the ocean from the time when these oceans were cut off from the atmosphere and from mixing. And certainly in their wake, we have a very rich nutrient cycle, which leads to, probably back during the Paleoproterozoic, leads to these big algal blooms and that type of stuff. And this is, of course, a little documentation of what these little organisms probably look like. This is jellyfish, and we have some very native plants, which you see from this time. And of course, these were, of course, all multicellular, and this started to rise in the Ediacaran, which was immediately after these global glaciations. A very significant time, and very, very interesting to study into many different reasons. So with that, I will complete this lecture and keep it short. And I just wish to say thank you to my Polonaise program from NCN and the European Union, which assisted me in this project, as well as the EDU-ARCTIC for giving me the opportunity to present here. And of course, I wish to thank Paul Hoffman and Snowball Earth for providing me with a lot of the lectures. So that's everything I have for you today on a very brief introduction to Snowball Earth.